6.4 exponential growth and decay. All right, so here is our exponential growth formula. The A is going to be the initial amount. So, you know, if we're putting money into a bank, that's, say you put $100 into the bank, that is going to be the money that you, $100 that you put in. The Y is going to be the final amount. So you might earn some interest, and then after a certain number of years, you take out a larger amount of money, and Y is going to be that larger amount of money. Okay. The R is going to be the rate. Okay. And a note about the rate, it's going to be a percentage, right? So you might earn 2% interest or something on a bank account. And the rate, you want to, when you use it in the formula, you want to write it as a decimal. Okay, so let's say that you know that the rate is 12%. Well, you'd want to write that, you move the decimal 2 places to the left. The decimal's right here right now, so you move it 2 places to the left. That'd be 0.12 written as a decimal, and this is the version that you'd want to use, okay, when you're doing your calculation. And then the last part is the time. T is for time. Okay. All right, so let's try it out. Funky Town has a population of 20,000, and the population increases at 4% per year. So first we're going to just write an equation, an exponential function modeling the population over time. So we don't know what the, well, we do know the beginning amount. I'm using this formula here. We don't know the final amount because we don't know how much time we're talking about, but we can plug 20,000 in for the initial amount, all right? And then I've got 1 plus the rate, and remember that rate, you're going to want to write that, it's 4%, but we want to write it as 0.04. So I've got 1 plus 0.04, and then the T would be the time. You could use an X up here if you wanted to write it with X and Y, but I'm going to write it with T. Okay, and then I want to simplify this a little bit. And there's not too much simplification that you can actually do here. That's it, okay? Now some people are going to look at this and say, well, wait a second, can't I multiply 20,000 times 1.04? Well, you can't do that because they actually have different exponents. The 20,000 is raised to the first power, and the 1.04 is raised to the t, so I can't combine them because I don't know what t equals. So don't multiply these together. You can't do that. If you think about PEMDAS, you'd have to do the exponent before the multiplication, and I can't do the exponent because it's a variable. I don't know what t equals, okay? So that's as far as we can get on part A, all right? Now this says, what will the population be after 12 years? Well, now that I have this equation written, I just have to plug a 12 in for the t. Okay, and then I want to use PEMDAS, so I'm going to do the exponent first. I'm going to do this part first, and I'm definitely going to need a calculator for that. Okay, so I've got a calculator here, and that's 1.04, and there's this little arrow up key is my right here is my exponent key to the 12th, and I've got this number about 1.601, something like that. Okay, so when I'm writing this down on my paper for this step, I'm not going to write out the whole decimal, but I still have that whole decimal in my calculator. So that's it's important to try to avoid rounding as you go. It's okay, like, you know, I rounded that there, but I still got the whole decimal. I'm going to use that long decimal to get my final answer. So then I'm going to multiply this number by 20,000. So try to, if you round as you go, your final answer will be farther and farther off the more rounding you do. So I try to wait till the end of the, and I usually round my final answer, but I wait till the final, till I get to the final answer. Okay, so since we're talking about population, I'm going to go to the nearest integer, so I'm going to round that up to 32,021 people. So it's roughly that. I'm still putting this about equal because that indicates that this is a rounded number. You can't have 0.6 people, right? So I'll round that to the nearest person. Okay. All right. So for the next part, it says, when will the population reach 70,000? So I'm taking the same equation that I wrote in the first part, but the 70,000 is going to be the final amount. So I'm going to plug in 70,000 for the final amount here. Okay. And I'm going to try to figure out what t would equal to make this work. Okay. So what I'm going to do first is divide the whole equation by 20,000, because I'm trying to isolate the t, and I can partially do that by dividing both sides by 20,000. Okay, so then these would cancel, and then all my zeros are going to cancel here, right? So I'm just going to be left with 7 over 2, which is 3.5. Okay, and now at this point, I don't have a good way to isolate the exponent. You can isolate it with logarithms, but we haven't gotten there yet. That's a topic for later. So what we're going to do now is a guess and check thing. I'm going to just try plugging in different t values and have it come out to 3.5. So I'm going to take 1.04 and raise second and see what happens. It's still a pretty small number. So let's try raising it to the 10th. And it's still only 1.48, so I'm going to try to the 100th. And I'm just trying to narrow in on it. Okay, so now I'm at 50. I was looking for it to be 3.5, right? So I way overshot it when I went to 100, but I know it's something between 100 now. So let's try raising it to the 20th, see what happens. Okay, we're getting closer. Let's try to the 30th. And that's getting a lot closer now, and so I don't know, maybe I'll try to the 35th. See what happens. So I'm looking for 3.5. It looks like it's going to be pretty split evenly. It's going to be somewhere in between 3.2 and 3.9. So then I need something between 30 and 35. So I'm just going to keep narrowing in on it with guess and check. So I'll try 33. Okay, that looks pretty good. It's a little high, so I'm going to try 32. And that's pretty darn close, right? So I think that's as close as we're going to get from a nice round number. And this is just approximately, but it would be about 32 years. So it's not the most elegant way and the most precise, but you can do guess and check to kind of narrow in on those ones. Okay, when you have an exponent that's a variable. All right. Okay, so let's move on to the next one. If $200 is invested at 4% interest for 10 years, what is it worth? Well, we don't know the final amount, but the initial amount is going to be 200. I'm using the same formula from the top. And then I got 1 plus r. And it's tempting to put in a 4, but I want to use 0.04. Right? 4% is written as 0.04, and the time is 10. Okay, so now I got this. All right, so I'm going to start inside the parentheses by simplifying that. Okay, got it down to this. Next thing I would do is you got to do the exponent before the multiplication. Got to follow PEMDAS. Okay, so I'm going to work to the right here because I ran out of space. So let's see. I'm going to have 200 times something. Let's see, 1.04 to the 10th. So that's about 1.48. Okay, so this is rounded here, and I'm taking this long decimal there and multiplying that by 200 for my last step. Okay, and since we're talking about money here, anytime I'm talking about money, unless it says to round to a particular place, I round to the nearest cent. So we've got $96.05 there. Okay. All right. So that was exponential growth. So we used a formula that looks very similar to this. It just had a plus sign there instead of a minus sign. When you have decay, that means the money is going to be going down exponentially over time. Then you just subtract the rate instead of adding it. So it's pretty much the same formula, just with that with a minus instead of a plus. Okay. So an example is a car. It starts off expensive. Well, this is a cheap car, I guess, but it's going to go down pretty quickly after that. So this says the car depreciates at 7% per year. Okay. So that 7%. Now I know my rate is going to be 0.07. That's the number I'm going to use there. Okay. So using this formula, my initial amount is going to be the 15,000. Okay, and then I've got 1 minus 0.07, and then the time is, so I'm going to leave that as t. Okay, and then all I can do is simplify inside the parentheses here. So 1 minus 0.07 is, let's see, 1 minus 0.07. That's going to come out to 0.93, right? So 0.93. And there's my equation. And it kind of makes sense with the 0.93. That means if it's going down 7% every year, it means it's going to be worth 93% of what was of what it was previously worth, right? Okay, so what's it worth after 9 years? Now I can plug in 9 into that equation that I just wrote. Okay, and going to do the before the multiplication. So let's see, 0.93 to the 9th is about 0.52. Okay, and I'm going to use the nice long decimal and multiply that by 15,000. Okay, and we're talking about money again, so I'm going to go to the nearest cent. So $7,806.17 it's going to round to. Okay. All right, let's try another on the next page. We've got a new phone that's going to be depreciating in value over time. I'll put my calculator up here. All right, so since this is depreciating, that means the value is going down. That means we want to use the decay function here. I'm using this formula, okay? It costs $600 to begin with. And then the rate is 31%. And remember to write that as a decimal, so the rate is going to be 0.31. Okay, and then the time is 3 years. Okay, and then I got everything I need there, so let's start with the subtraction. 1 minus 0.31, well, that's like 100 minus 31 would be 69, so this is going to be 0.69. Okay. And then we want to do the exponent for the multiplication. Most common mistake I see is people multiply before doing the exponent, but then we wouldn't be following PEMDAS. All right, 0.69 to the third is this number. It's not that long of a decimal. I guess I'll just write this whole thing here. And then I'll multiply that out. And I should get my final answer, which I'm going to round to the nearest cent. Okay, so I'm going to take this decimal, multiply it by 600, and I've got $197.11. Okay. All right. Okay, a common ratio is what you multiply by to get from one y term to the next when the x's are evenly spaced. So what I mean here in this table, these x's are evenly spaced. 0, 1, 2, 3. Okay. We talked about this a little bit in the section, or a previous section. I can't remember if it's the last one. Exponential growth functions, the common ratio is going to be greater than 1. Okay, and for a decay exponential decay function, the ratio is going to be less than 1. Okay, so on these questions on the bottom of the page, it says, does the table represent exponential growth, exponential decay, or neither? So if it doesn't have a common ratio, then it's going to be neither. But if it does, then I have to decide if it's going to be growth or decay. All right, so let's take a look at these. So I'm looking to try to see what am I going to multiply by to get from y term to y term. All right, and you might notice these are getting smaller. So like if we're looking 16 to 4, well, we'd be dividing by 4, right? So, and that actually works with all of these. 64 divided by 4 is 16. 16 divided by 4 is 4. 4 divided by 1 is 4. Sorry, I'm dividing by 4 to get from one to the other on all of these. So you're dividing by 4, but that's not really the common ratio. So you want to think about what are you multiplying by? Well, dividing by 4 is actually the same as multiplying by 1/4. So we're multiplying by 1/4 on these, okay? So another way you can find the common ratio is just to take any of these y values except the first one, and then divide by the previous two. So I'm going to take 16 divided by 64, and that comes out to 0.25, which is 1/4, right? So you can say the ratio is 1/4 or 0.25, but I do have a common ratio here. Now this ratio is less than 1, so then I know it's decay. So this one is going to be decay for that reason, okay? If the x's are increasing as the y's are decreasing, that's a indicator that it might be decay. You still would need to check if you have a common ratio at all. But so if we look on this one, the x's are getting bigger and the y's are getting bigger too. So I know it's not going to be decay. I'm thinking it might be growth, but I still have to check to see if I have a common ratio. So I'm looking for a pattern here with my y's, and I'm thinking, am I multiplying by the same thing to get from y term to y term? Well, 3 times 2 would be 6. 6 times 2 is 12. 12 times 2 is 24. So I do have a common ratio. That common ratio is greater than 1. So that means I do have growth here, an exponential growth function. Okay. On part C, so I'm looking, hey, these are getting bigger and these are getting bigger too. So I'm thinking maybe growth. It's definitely not decay. But let's check for a common ratio. So I'm thinking 7 times something is 10. Well, let's do 10 divided by 7 would give me that ratio. Okay, so it's that decimal. Well, let's try 13 divided by 10. And then 16 divided by 13. So it's not the same thing. We're multiplying by different things to get from term to term here. So there is no common ratio. In this one, there's actually a common difference. We're adding by 3. You might have noticed that already. So this is going to fit a linear function, not an exponential function at all. There's no common ratio. And since there's no common ratio, that means I've got neither. It's neither decay or growth. I could say it's linear, but they didn't ask me. They just asked if it's decay or growth. Okay, so you can tell with these tables if you've got growth or decay if your ratio is more than 1 or less than 1. If you have an equation, like on these two, I already have equations and I just want to check if these are exponential growth or decay. Well, you can look at the base. So it's going to be, if the base is greater than 1, then it's going to be growth. And if the base is less than 1, it's going to be decay. All right, so then you just have to know, well, what's the base? Well, the base is the thing that has the exponent on its shoulder. So my base here, this is my base. The 3 is my base here. That's my base, okay? Over here, the 0.9 is the base. So that's the only part I really need to look at. The 0.2 is a distractor, and so is the 8, and so is the -4 and the +7. That's the only part I need to look at to figure out if it's going to be exponential growth or decay. So this is more than 1. That means I've got growth for this one. This one, 0.9 is less than 1, so I've got decay for that one. Okay. All right, so new topic. We're going to look at compounding. So the compounding is the interval at which interest is added to the original amount. So I'm just going to think of this as a bank account just for just to get started. So when I say interest, it's what percentage. So if you've got $100 at 5% interest, if it's just stated like that, that probably means at the end of 1 year you're going to add the 5% into the bank, and then you'd have $105 because 5% of 100 is $5, right? But you don't have to you don't have to add that percentage back into the account at the end of a year. You could do it at any interval. And that's where you need the compound interest formula, okay? So this looks a lot like the exponential growth formula that I showed you, but we've got these n's in here. And the n is going to be the number of compounds per year. Okay, so you could actually use this for just basic exponential growth. It's just if you're doing your compound once per year, if it's annual interest, then those n's would be 1, and then this would simplify to 1 plus r, and the exponent would just simplify to t. Okay, but you can also use this version with the n's when you have a number of compounds that isn't once per year. Okay, so number of compounds on this example down here, when we're talking about annually, that means we're going to compound once per year. So n is going to be 1. Semi-annually, think about semesters in the school year. There's 2 semesters, right? So that means there's going to be 2 compounds per year. You're going to compound at the end of each semester. Okay, monthly, well, there's 12 months in the year. Okay, so we're going to call that 12. Daily, we'll go 365. Let's just forget about leap year. Okay, I guess technically it'd be 365.25, but let's just go with an even 365. Okay, so let's start setting this up. This says $100,000 is invested at 6% interest, so I want to keep in mind my rate is going to be 0.06 as a decimal, right? And then this is going to be the time. We're going to use 9 years for the time. And we're going to find the ending balance, okay, for each of these. Now, the more often you compound, the more money you should have, okay? So we should get the least amount of money when we're putting the 6% in at the end of 1 year, and then we should get more if we're putting the 6% in more often, okay? All right, so let's try this out. So for this first one, you can actually just use our basic growth formula. So I'm just going to use this here. I don't need the n's because if the n's are 1, it's going to simplify to this anyways. So my initial amount then is 100,000, and I've got 1 plus 0.06, so I'm going to call that 1.06, and then 9. Okay. All right. So let's try it out. Here, I'll get my calculator up here. Going to do the exponent first, so I'm doing this part first. There's 1.06 to the 9th, and then I'm going to multiply that by 100,000. And I've got, let's see, that's $168,947.90. I'm rounding to the nearest cent. Okay, so we should get a little bit more than that if we're compounding twice per year. So for the rest of these, I'm going to use the formula with the n's. So I'm using this formula, okay? So let's see. Initial amount is still 100,000. Almost put 10,000, that would have changed things. And then 0.06 is the rate, but now that's the numerator, the fraction. The denominator, n, is going to be 2. Since it's twice per year, and then there's also another n up there. Don't forget about that one. And I've got this. Okay. All right. So this is a little bit harder to simplify. I'm going to start with simplifying this. So I'm actually going to start with the 0.06 divided by 2. Okay, 0.06 divided by 2 is 0.03. And then I'm going to add 1 to that. So 1.03 is going to be the contents then of the parentheses. Okay, 2 times 2 is 18, so I'm going to write that that exponent is 18. And then I would do the exponent next, so 1.03 to the 18th. Okay, and then I'm going to multiply that by 100,000. And let's see, I'm going to write this over here because I can see I'm going to be a little short on space here. And I'm rounding to the nearest cent. So hey, I do have more money than I had up there, right? 168 to begin with, and now I've got 170. So a little extra money when you compound more often. All right, let's try monthly now. So I'm using the same formula here with the ends. So initial amount is 100,000. Still got my rate at 6%. It's just now the n is 12. Okay, and the time is still 9, so I got 12 times 9 as the exponent. Okay, so again, I'm going to start in here. I kind of start with that fraction and work my way out. So 0.06 divided by 12 plus 1. So 1.005. Okay, and then let's figure out what 12 times 9 is. Here we go, it's 108. All right, and so now I'm going to do the exponent, 1.005 to the 108th. It's a big number. Well, no, it's just a small number because we're just taking a very small number and raising it to that exponent. And then we're going to multiply by 100,000. Make sure I get the right amount of zeros there. Okay, and on this one, we're going to wind up with $171,369.95. Right? And yeah, hey, more money, the more often we're compounding. So let's try daily. Just the n's, same as the last two parts B and C, it's just the n is going to now be 365. Okay. So let's see, we've got 365 times 9 up there in the exponent. Okay. All right, start with this fraction again, 0.06 divided by 365, and then add that to 1. My calculator went to this, you see this e to the negative fourth? It went to scientific notation. This means times 10 to the negative fourth. So the decimal has really moved 4 spots to the left. This is a very small number. But just use that number. You don't have to worry about that. Just keep doing your calculations to that number in your calculator. I'm going to add 1 to that. And so you see that number I had before was 0.00164, and then I just added 1 to it. Okay, and let's see, 100,000. Just write out this whole thing, and you want to try to avoid rounding as you go. And I'll take 365 times 9 to simplify the exponent. Okay, and now I'm ready to do the exponent. So I've got that long decimal. Got that decimal raised to the 3,285th. Okay, and then the last thing is to multiply by 100,000. And on this one, got that much rounded to the nearest cent, and if you check that, it is we do have more money, right? A couple hundred extra dollars and some change. All right, that's the end of the section, and I'll see you next time.